Practical DICOM, Module 2, Medical Informatics Standards. In Module 1, we had an introduction to digital DICOM. And in this module, what we're going to look at is more in-depth DICOM and how it actually works. Module 3 will go over Healthcare Language 7, or HL7, and HL7 FHIR, which is the rapid transfer of data using HL7 over the web. This will also cover the new regulations about mandatory implementation of HL7 FHIR by the federal government, how, when, and why. Now we'll begin Module 2, Standardization of Medical Imaging, DICOM. The world of medical imaging is changing rapidly, and we want to benefit from progress, but how do we choose to adapt to the changes that are constantly happening within healthcare informatics and those changes that are now being mandated by the federal government? One of the big questions in hospital healthcare in the United States is, very simply, who's in charge from the local level to the national level? Standard policies, procedures, and protocols help us navigate through this chaotic mess called healthcare system information. These policies, procedures, and protocols are evolving to reflect the changes in equipment manufacture and also practice of medical imaging. DICOM is a standard that helps interface equipment or modalities that capture medical images and allow those modalities to share information. DICOM is married to HL7, Hospital Language 7, so that the information contained can be transferred between equipment, both text and images. Hospitals and their equipment are heavily regulated and have a lot of standards and policies and procedures they must adhere to. We can see that there are over 629 federal requirements for hospital regulation, let alone the local, state, and national requirements, and the Joint Commission requirements. To receive any kind of reimbursement from the CMS or federal government system that regulates Medicare, Medicaid, and other entities paying hospitals, the hospital must be approved by the Joint Commission. This includes medical imaging, and this is why DICOM is so important. Healthcare is one of the most regulated industries in the United States, and the result is this regulation can be time-consuming, require large amounts of administrative work, and many controls are necessary. Obviously, it can be very costly, and flawed regulation and standardization does more harm than good. Innovation and technical progress may be slowed by the regulatory process, and it also impacts on the competition between hospitals and manufacturers of medical equipment between each other. Standards and specifications represent knowledge in the form of regulations and guidelines that are documented. The implementation of standards varies dramatically from facility to facility. Policies and procedures and protocols for medical image vary from department to department. Some benefits of standardization are as follows. It improves clarity, and every individual is able to realize that a standard process will eliminate the need for guesswork. It also includes productivity in all areas that it is embraced. Standards, policies, and procedures for medical equipment usage are department-specific. The National Electronic Manufacturers Association, which has standards for manufacturers of medical equipment, provided the first standards for X-ray in 1926. This means that it has been developing medical imaging standards for more than 90 years. DICOM. While the focus of DICOM is diagnostic imaging, the standard was developed with the capability to be extended and expanded in modular fashion to support new applications and incorporate new technology. New DICOM standards incorporate both lab and other images. What does it mean to be DICOM compliant? A DICOM device can be anything from a reading station to a preliminary review station in the CT or MR scanner. It can also be a computed radiography laser reader, a tape archive, or a DICOM gateway. But the label DICOM alone does not tell you which provider classes the device supports. So how do we know which portions of the imaging system are compliant with DICOM? Manufacturers must provide to users or customers a DICOM compliant conformance statement to illuminate just that question. How does the equipment work, and which pieces of equipment can it interface to? In-depth understanding of the DICOM standard requires some familiarity with medical imaging, linguistics and semantics, computer science, and engineering. Fortunately, a working knowledge of the practical aspects of DICOM should be sufficient for most users. For many years, the DICOM version standard 3.0 was considered the correct standard for DICOM usage. Today, we just look at the DICOM standard, not by version, because the DICOM standard can be seen on the internet and it can be accessed at any time with all of the updates by those that oversee DICOM conformance standards, DICOM equipment standards, and DICOM service class specifications, and all the portions that create DICOM, Digital Imaging Communications in Medicine. Let's take a look at how DICOM is used, or the data exchange mode. What we're looking at is we start with the World Wide Web, the www domain. This is the network we use to exchange and transport information. All the data that comes out of the DICOM archive has to pass through a DICOM module gateway to match up both images and text. Once matched, this data can be sent across the World Wide Web. Remember, the images sent across the World Wide Web are a combination of both images in DICOM and language in HL7 that have been married. Here we see a digital information and communications in medicine model. The data being transmitted is the patient's personal data, the study information data, and a description of the clinical image series. Also, the image data describing the clinical images, both the mode like CT or DR, and pixel definitions are included in the information sent through the model. Let's take a look at that process. We have different steps such as query, finding out who the patient is, what the study is, how to move the study. These are called subject-objects pairs, or SOPs. It tells you a subject and what you need to do with it. This goes to the DICOM client. Information then goes to the DICOM server, and from the DICOM server we go ahead and request the information from the PACS archive. The PACS archive then takes and retrieves the information and pushes it back to the DICOM server, and the DICOM server then sends the information that it has pulled back out to the network to be utilized. These are output files. The output files are transported through the TCP or transport protocol, and they are converted into CGIs or computer graphic interfaces. It often becomes a problem for people if they don't understand the difference between a service class user and a service class provider. The big thing is that any piece of equipment can be a user or a provider or both. Service classes defines what a system can do. If a system has not been set up with a certain class, it will be unable to form or perform the function in that area. This means that a system that claims to be DICOM compatible may be compatible only in one area and only can communicate in that specific area. Let's take a look at this a little bit more practically. A laser printer can only do what? Print out images. It cannot provide images, so therefore it is a service class user, using the data from the service class provider. And the service class provider may be either a CR, a DR, CT, or other type of equipment. A DICOM storage class provider can provide images in the DICOM file format. It provides these images over a network with a DICOM compliant protocol, TCP/IP, or Transport Control Protocol/Internet Protocol. Therefore, it can push images to things like a DICOM compliant laser printer, which, as we discussed, is a storage class user. A CT scanner works as both an SCU, service class user, and an SCP, service class provider. It pulls data from other areas and it pushes the completed exam out back to new areas. So we begin by pulling in data, we then work with the data and convert the data, and then we push the data out in its new format to other users. This information is pushed or pulled using what's called a DIMC. A DIMC is data that is either composite, meaning it is more than one piece of information or a couple of SOPs, or it is a single action. So the couple of actions put together forms a function, and this is called a DIMC-C, whereas a simple action like get, set, store, find is a DIMC-N or normal. There are 5 DIMCs that are used for composite information objects called DIMC-C, and there are 6 that are used for normalized information objects. DIMCs are used in the transportation of data. Let's look at some of the commands we have in our DICOM toolkit. The command image contain implements DICOM image archival or storage. It uses the application entity, which is the information about the patient and also about the host and the port. And what we do is store the information, retrieve the information, or query the information. So I can query or find whatever information is in the application entity, and once I find it, I can go ahead and do what? Retrieve it. So the Image DICOM toolkit is used with the PACS archive to find, store, and retrieve data. Now let's look at the DIMC-C service, or the functional services or composite service that are DIMC. Take a moment and read the different requests or service requests using composite DIMC services. They are C-Store, C-Find, C-Get, C-Move, and C-Echo. By composite, what we're going to do is find this, store this, get this, and whatever the this is the object of the function. And that is called a service object pair. Notice with DIMC-N services, they are the same, get, set, etc., except there is no object attached to these. So in DIMC-C or composite, we have a service object pair. In DIMC-N, we just simply have the service or action. Now let's take a look at this graphic again and have you take a look and see, can you see which are DIMC-C and DIMC-N functions and services? Image Contain accepts the SOP classes of Storage Service Class and Query Retrieve Service Class and maintain the database. This command also has a never exists status, which means it cannot be applied to certain functions and things that are happening within the computer system. Store SCU implements SCU for Storage Class Service. It connects to Storage SCP, so that is Service Class User and Service Class Provider. Find SCU is the Service Class User, and it implements SCU Query for a Retrieve Service Class, and it supports querying using C-Find. Next, we look at Move SCU, Move Service Class User, and let's see how that's actually utilized. Now let's see how we use the different DIMC services and what we use them with. Here is a graphic which shows the SOP or the DICOM service pair, and what we're looking at is the service DIMC is being store what? The CT, information object definition. The generic sentence would be, or the SOP class, store in a CT, and the specific instance would be store this image in the CT. The SOP class is the elemental unit of DICOM. Everything that DICOM does is based on the use of SOP classes. So let's take a look at DICOM SOP classes. The entity that initiates use of a service is known as a service class user, and the provider is known as a service class provider. When setting up a DICOM connection, there is a negotiation process where it becomes clear what capability the device supports and what it does not support. Those capabilities are clearly specified and identified in the standard as so-called SOP classes. The storage SOP class is the DICOM data workhorse. It is responsible for moving DICOM images and other data between applications. The storage SOP classes are made up of the data that needs to be stored and the composite service C-store. Let's take a look at some of the examples. For example, nuclear medicine, ultrasound, MR, and X-ray. Now let's take an overview look at the DICOM file format. It is a single file that contains a header and image data. The header, which stores information about the patient's name, the type of scan, image dimensions, etc. And the image data is the data of the image itself. Is it compressed? Is it not compressed? What about the bitmap? And what type of storage? GIF or JPEG? These give us a lot of information. So if we're taking a look at image data, is it compressed or uncompressed? In other words, did they get rid of some files because you didn't need them? And according to the American College of Radiology, you cannot compress data more than 3:1. What about the bitmap? The bitmap is where the shades of gray are actually mapped on the matrix to create the image. The DICOM file header. The DICOM file header requires a 128-byte preamble, usually set to 0. DICM letters come next. The rest is the real header information in groups. For example, group 002 hex is the file metadata for the information group. Let's see what kind of data we can find in this file header. Well, first of all, we know that the modality is an MRI, and its manufacturer, the slice thickness, the software version, samples per pixel, number of frames, number of rows, number of columns in the matrix, bits allowed and bits stored, and what is the highest bit number used in that matrix. So in the header, as you can see, there's a lot of information. Let's take a look at the different types of DICOM data. We have information object data, a data abstraction class of real-world objects, like a CT scan. Next, we have the DIMSI, which we've already reviewed, or DICOM Message Service Element, the set of DICOM application layer communication services. We have DIMSI-C and DIMSI-N. Next, we have the DIMSI Service Group, or DSG. It is a subset of the full DIMSI services, which is applicable to a specific IOD, or the image object definition. So what we're looking at is the service object pair, SOP, is equal to the IOD, which is like CT scan, plus the DSG, or DIMSI Service Group. So we can say, move the CT scan images to the PACS archive. Or we might have get CT files for CT exam to be performed. Let's take a moment to look at the patient identification attributes. Notice we're looking at the patient ID, and in the patient ID we have different tags. Each tag is specific to a certain attribute, such as patient's name, patient's ID, etc. Each of these attributes has a full description, so we have a full description of what a patient ID would be. We have a full description of what other patient IDs are available. Put it all together and you have the patient identification. The application entity is a term used for the software application capable of using the DICOM services. Each component of a system, such as an MRI scanner, will have its own AET. Along with the unique identifier for the hospital, this gives every image taken in the world a unique identifier. All components of the system are programmed with an AE list, called AEL, and this is a list of the other components that they are allowed to exchange information with. So basically what we're looking at with the AE title is this is a GE CT scanner at Memorial Hospital Southeast, and it can identify and interact with the printer, the workstation, etc. It also cannot interact with anything that is not on that list. So basically the AEL, or list, is a list of equipment that CT scanner can interface with or talk to. Association services, or a handshake or a greeting between the different equipment, the interface. Before everything, association establishment must be done. So when someone wants to get information from the CT, they need to be at a workstation, and they can call this workstation a service user. So the service user does a handshake with the CT so that it can exchange information. The service user has to request the handshake. The initial information includes the application context, the DIMC specific user's information, the DIMC service information, and presentation and session requirements. Association services. A. Associate. Service is invoked by a DIMC service user with the related parameters to establish an association with another DIMC service user. Association release is done using a release and a abort. In other words, when we want to end the handshake, we have to tell them, hey, let go or stop it. So now let's take a look at the DICOM information model. This is a model of how information or data goes through the DICOM service. So we can see the service class specification goes to a specifics related box, which asks for the SOP. Once we hit the SOP and have it defined, we then have to go to the service group. We have to also go to the information object group, where we look at the DIMC services being performed and their attributes. The attribute or data element is the functional unit of DICOM. The DICOM data element is comprised of a tag that identifies the element. Value representation describes how the field to follow is being represented. The length that gives is the length of the value field that it follows, and the value field that contains the value to be transmitted. Next, we can see how DICOM is actually divided up into different areas or parts. We're going to take a look at each one of these parts or areas. We'll start with Part 1 of DICOM. Part 1 of DICOM is the document that provides an overview of the rest of the standard. It provides a description of the design principles, it defines many of the terms used, and gives a description of the other parts. Part 2 is the definition of conformance to DICOM and what conformance means. Rather than provide a specific list of items that every type of implementation has to follow to be conformant, DICOM offers a number of building blocks such as SOP classes and requires manufacturers to describe unambiguously how their products actually conform to DICOM. Part 3 describes how information objects are defined. It then goes on to define the information object classes that are used in DICOM. Part 4 of DICOM contains the service class specifications. The services can be thought of as the operations performed on the information objects. The roles of the SCU, Service Class User, and SCP, Service Class Provider, are also defined in this part. The two columns of the table above are important. The left column is a list of IODs that are composite objects, and these objects contain attributes that are related but not inherent to the real-world entity, plus those that are inherent. The right column lists the IODs that are normalized objects. The left column of the table above is the annex of Part 4 that specifies the service class named in the right column. The storage service class provides the basic support for transfer of images between DICOM applications. For example, to retrieve images from DICOM applications, the Query Retrieve service class supports basic operations to access and move images based on simple search criteria. Once a DICOM application assembles a data set, it must be ended so it can be put into a message form for communication. This encoding process is specified in Part 5. This is the main function and can be thought of as the language that the entities use to speak, or the two devices use to speak to each other. At the most basic level, all information objects are composed of data elements. These elements encode the values of the attributes described earlier, such as patient name, number, bits per pixel, etc., to turn an information object from an abstract entity to an instance that represents something in the real world. Values are supplied for the data elements. Part 6 of DICOM is a complete listing of all data elements along with their numeric values or tags, their text names, what their representation is, and whether they contain one or more items, and what the allowed values are for those elements that can only take on certain values. The user of a piece of medical equipment interacts with the software that translate his or her input into the data and commands used by the equipment. In communication, this software would interact with the application layer of the communications protocol. Part 8 defines the network support for exchange of DICOM messages. Currently, TCP and ISO-OSI protocols are supported, but the nature of the upper layer service defined in this part is such that it should be possible to expand to other protocols with relative ease. We'll talk about that in the next module when we look at HL7 and HL7 Fire with application programmable interfaces. A long time ago, when we first started with DICOM and ACR NEMA, the first versions of the ACR NEMA standard defined a high-speed parallel data interface. This was known as a merge box and allowed one system to talk directly to another system. They're plugged in to each other. Here we see the DICOM merge box and the cable that allowed it to plug in between two devices. To allow to connect to older equipment, DICOM Part 3 had the Part 9, which was a description of how the devices would directly plug into each other, or point-to-point protocols. Next, we'll look at DICOM conformance statements provided by the manufacturers about their equipment. When you find that there's an error with your equipment, you can troubleshoot using the DICOM conformance statement as one portion of the analysis. Users can request DICOM conformance statements from their vendors. These conformance statements are especially helpful in finding network solutions to interfaces and other problems with your equipment. Conformance statements allow you to check the service class user and service class provider. Here we can compare the scanner and workstation by using the DICOM conformance statement document. So let's take a look at interfacing a PACS viewer with other DICOM compatible devices. To integrate these devices into our network, we'll need to take a look at the DICOM conformance statement for each piece of equipment and establish an association with the modality and the DICOM server. Once we have established this interface or association, we need to map the DICOM data included with the DICOM object to fields in the PACS viewer database. Conformance statements tell you quickly the DICOM capabilities of given equipment in a way that allows for easy comparison at a very basic level. With a conformance statement, you can easily spot incompatible X-ray and office equipment. Here we see part of a GE conformance statement standard for one of their CT scanners. The abstract syntax field provides the name of the CT image storage SOP classes that can be performed by the modality. Reading from left to right, you will see the user ID, UID, for the subject-object pairs class and the various transfer syntaxes that the modality supports or proposes. The fourth column or last column is used to relay any extended negotiations that can or will be performed during the association. A major issue for any standard is determining conformance. In many situations involving public health and safety, conformance to standards is required by law. For many other types of standards, including DICOM, the conformance is voluntary. The DICOM interfaces and what the CT scan or other modality can do may differ between manufacturers because, remember, conformance to DICOM is voluntary. To reduce errors in the association, the patient's ID number and test accession number are already in the machine and connected with the test about to be performed, reducing errors. Also, having these numbers in the machine enhances security because fewer people can handle the data. Any vendor or manufacturer claiming that their equipment or software conforms to the DICOM standard must be able to provide a conformance statement that describes exactly how that device or software conforms to the standard. Obviously, manufacturers don't want to give away their design and secrets, so in some cases you will find that there is a proprietary number in there, meaning that the manufacturer does not want to give you that information for that particular area. The main reason for that, of course, is sales. Each manufacturer wants to sell their equipment based on the features or software based on the features. If you think about the physics of medical imaging, A CT scanner is a CT scanner is a CT scanner. It's how we configure the CT scanner that makes a difference. Because the conformance statement enumerates all that DICOM applications have to do or define, anyone wishing to gain a deeper understanding of DICOM would do well to read the part of the standard on conformance after reading the introduction. Basically, all we want is DICOM in and DICOM out. In the process of using the equipment, how the equipment works and how it handles data is the manufacturer's proprietary system knowledge. We want to just make sure that the equipment receives DICOM data format and that the equipment, on finishing working with that data, puts out a DICOM data format. Not only does DICOM store the image pixels, but it also records a multitude of other image-related parameters, such as patient position, physical sizes of objects, slices, exposure parameters, etc. DICOM supports up to 16 bits or 65,536 shades of gray for the monochrome image display. The display is created in the equipment using lookup tables, and then this is exported out in a DICOM format. DICOM provides a complete encoding of medical data. DICOM files and messages use about 4,000 standardized fields, which you can look up in the DICOM dictionary. So let's see how exam works. The user requests the exam in the hospital information system, and if that exam is a radiology or imaging exam, it is picked up and sent to the radiology information system. If it's a lab exam, it goes to the lab information system. The radiology system automatically schedules and organizes that data for the exam. That data for the exam, once it is scheduled, is put into the operator or radiographer's work list. The operator or radiographer then performs the examination. When the exam is completed, it moves the data to the radiologist's work list for radiology analysis and a reading. When the radiologist completes the reading, the data is sent to the hospital information system and it is deleted off the radiologist's work list. To be able to accomplish this, the data, which is comprised of both images and text, has to be in the DICOM format. Thank you for your time and watching. You can find more information in subsequent modules and previous modules on healthcare standards for medical imaging. Thanks for watching. Working with DICOM, this is Module 2 in a series on standards for DICOM medical imaging and informatics.